Good morning, everyone, and thank you for joining us today. Today's presentation is being brought to you by the Transportation Learning Network. TLN is a program of the Upper Great Plains Transportation Institute at North Dakota State University and is a partnership with the 4 state DOTs of North Dakota, South Dakota, Montana, and Wyoming, and the Mountain Plains Consortium, which includes 8 universities in Colorado, North Dakota, South Dakota, Utah, and Wyoming. A little bit more about the Mountain Plains Consortium. Its theme is transportation infrastructure and operations to support sustainable energy development and the safe movement of people and goods. MPC is a competitively selected university transportation center sponsored by the US DOT through its Research and Innovative Technology Administration, and NDSU Upper Great Plains Transportation Institute is proud to have received that UTC designation. Our speaker, again, we're pleased to bring in Dr. Panelides. Chris is a professor of civil and environmental engineering at the University of Utah. His research interests include seismic design of structures, evaluation, and rehabilitation of reinforced concrete bridge construction. He is also interested in supplemental damping for structural systems, earthquake engineering, and fiber reinforced composite materials. With that, Chris, I'll turn it over to you to begin your presentation.
Oh, thanks, Chris. Thanks, everybody, for attending. Before I start, actually, I just want to start with this slide because, I'm a professor and without my students, I can't do anything. So Vanessa McEntee, I got her MS on this work from Boise, and Bhaskar Kunwar, who's originally from Nepal but now works here in West Jordan in Utah, were the students who did all the work. So the topic here is seismic repair of concrete wall piers using carbon fiber reinforced polymer confinement. And I'm sure all of you know what a concrete wall pier is, but I'll show you a few slides. So as an outline, I'll give a little overview of what a wall pier is. And I'll talk about the test that we did here. And I have here an as-built concrete wall pier, which means this was a concrete wall pier that was built with the standards before any seismic requirements. I have a modern code compliant concrete wall pier, which is a wall pier that actually meets the current seismic requirements. Then we built a couple of more specimens that are identical to the first one, the as-built, but we retrofitted it. The first retrofit was a vertical carbon fiber anchors, and then the second retrofit was carbon fiber near surface mounted bars. So you would think that we built 4 specimens and that would be the end of it. But of course, being professors, we like to test as much as we can. So we built these things that were large scale, about half scale. And so we thought, well, let's take the first test, which is the as-built concrete wall pier, after we tested it and failed it, and let's repair it. So after an earthquake, what would that first pier do if we were to repair it? So in the repair, we use a mild steel vertical near surface mounted bars and carbon fiber. So that was the repair of the as-built. And then we said, okay, now let's take the modern code compliant concrete wall pier. So that one that was designed pretty recently, and let's try and repair that one. So then we also repair that one, the modern code compliant wall pier. And to repair that one, we use headed steel bars, a carbon fiber reinforced polymer shell, and concrete grout, or what we affectionately call around here a donut. So you see that with 4 specimens, we're actually able to do 6 tests. So I'm going to describe these 6 tests to you, and I'm going to end with the conclusions. So here is a bridge built with concrete wall piers in Utah. And you can see these are typically found in rivers. And I'm sure in most of you in your states, you have something like looks like this. These were constructed before the AASHTO Bridge Design Code in the 1970s, mostly to support gravity loads. So actually, they are not designed for seismic loads, and we wouldn't expect them to do very well. So we built, as I said, a sample that would simulate something that exists out there. You can see our samples were pretty large. The wall height was 9 feet. The thickness was 1 foot, and we had some typical footings, 6 by 5 foot, and then we had an 18-inch footing. The steel ratio was low, much lower than what the current code allows. But the main thing we were looking for was these lap splices. These lap splices typically are not very long. You can see here is only 14 inches. They are not allowed by the current code, of course, because that is a major problem in seismic. You can see also the reinforcement. There is no seismic hooks. There is no good confinement of the plastic hinge, which would be down here at the bottom of the wall. And the bar spacing is very, very sparse. So all of these things, and in addition, there is no seismic hooks in the stirrups. These make it very, very uncomfortable for somebody to say this will perform well in an earthquake. But the major deficiency would be, of course, the lap splice reinforcement, which is very typical. So here you can see a cross section. You can see the bars are spliced there. And one thing I forgot to mention is the width of the wall is 48 inches. So it's a 4 foot by 1 foot wall. Here you can see pictures of the reinforcement. You can see it's very skinny. There is a lot of reinforcement up on the top, but that's where we're applying the load. We're applying it perpendicular to the 4 foot direction. So you can see it's an out of plane type of test. And here you can see we have the 4 specimens in our lab. So the way we test this, we apply an axial load, about 6% of the capacity of the wall. That's typical. And then we apply a lateral load at increasing drift ratios, as you can see here with this actuator. And that's how we keep track of how far the wall is moving in an earthquake. Here you can see it, for example, when it's moved about 5%. 5% of 8 feet is about 5 inches. So when it's pulled back 5 inches, you can see how it looks like. And then this axial load is applied with the rods reacting against the beam from a hydraulic actuator. So this is our cyclic loading. We apply 2 cycles at increasing drift ratios, anywhere from 0.5% to however far it can go. It's 2 cycles, and we found out 2 cycles is a good number, because if you do 3, you're fatiguing it too early. So you don't want to put too many cycles starting from the beginning, because as you can see, these cycles are getting pretty large. So it's displacement based, because you want to make sure you capture the peak force. Before we did the test, of course, we did some analysis. It's a static pushover analysis, and it shows you how much we expected this wall to go. The lateral force about 15 kips, displacement about 6 inches. The program that we use here is a little bit fancy. It's called OpenSeas. It's open software for earthquake engineering. It's available. It's open source. You can go to UC Berkeley and you can download it. But then you need a little bit of time to learn how to use it. So here's the first test. We failed the lap splices here at about 4% drift. And as we expected, the load was not very high. It was about 15 kip. Drift wasn't too bad, actually. It went a little bit further than what we thought, but it's definitely not performing, as I will show you, as well as the modern code detail wall. And here you can see why we know the lap splices fail, even though there's not a good picture. We see that the footing bar and the wall bar actually are very far apart. That means that the tension is not transferring the steel. And here you can see that our prediction actually wasn't too bad. It's the red line, and the blue line is the test. Now, the modern code compliant concrete wall pier, how good is it? Or how bad is the existing wall piers? So for this one, we built it according to the AASHTO LRFT code. We made sure we didn't have any splices here at the bottom of the wall. All the dimensions were identical for the footing, for the wall, but the cross-section, as you can see in the reinforcement, is meeting the code, meaning we have more than 1% steel ratio. We have good seismic hooks, you see, as the code requires now. The bars at the bottom hinge where the plastic hinge is supposed to form are very 4 inches spacing, which is very good, providing very good confinement. The bars also for flexure are number 6, so they're much bigger than the previous one. So, and everything is according to the code. So this one is a Cadillac compared to the previous one. So how well did this one do? You can see a picture of it here. You can definitely see here the confinement reinforcement, and you can see that these bars are definitely better detailed. There is no lap splice at all. So this one did very well. It went much further than the other one, but you can see it also sustained damage. And when you see the damage, you will say, hey, but this is damaged a lot. Yeah, but this one went to 10% or more. Actually went to, 10% drift ratio. So the other one, remember, only went to 6%. And the other one went to 15 kips. This one went to 30 kips. So it's day and night. It's almost double the performance. So you can see here some of the original things that happen. A 2% drift, which is roughly 2 inches. The rebar started yielding. At about 3%, we see that the concrete started cracking and spalling in this area that I showed you down here in the early days. And then at 10%, actually, we had a rebar fracture. We had a couple of bars that fractured on both sides of the wall. So you can see that, yes, this is much better performance than the as-built. And we kind of knew it, but we needed this point as a point of reference to see, well, how good is your retrofit? How good are you approaching this one? And in this one, my student got a little more ambitious and he did all the analysis. And you can see the analysis gives us a very good representation of the capacity of this pier. But I have to admit that this analysis was done after we tested the specimen. But then he got a little better, and not only did he predict the static analysis, but he actually predicted the dynamic analysis. So you can see this is cyclic, but if we want to throw this into a potential earthquake, we actually can do this now, and it will predict pretty accurately how well does the wall pier will do in a real earthquake if we throw the ground acceleration at it. Retrofit methods. So the question now is, how do we fix the deficiencies of the as-built wall pier before an earthquake happens? Okay, so in this project, we had some co-sponsors who were actually supplying materials mostly, and they said, well, why don't you use carbon fiber reinforced polymers? Everything else has been used. Why don't you try something new? And we said, yes, let's try that. How good would these carbon fiber reinforced polymers work? Now, a little side story here. I started working with carbon fiber reinforced polymers in the 90s. The Utah Department of Transportation found that a lot of the bridges on Interstate 80 actually had corrosion, and they wanted to postpone replacement of these bridges, and they were trying to buy time. Well, how do you buy time? So we use carbon fiber composites to wrap the columns and the joints and the beams so that actually they could buy time and replace those bridges in a more regular way, rather than trying to replace 15 bridges at once. So that's how I got introduced into carbon fiber reinforced polymers about 30 years ago. So at that time, we were doing it just for prolonging the life of the bridge. But then later on, we did some tests with the I-15 reconstruction where we tested a bridge for seismic. And then we said, wait a minute, these carbon fiber polymers, actually, they could be used to improve the seismic performance. At that time, UCSD at California, San Diego had done some tests on columns, and we followed their research, and we built on that, and we actually did some beam column joints at the cap beams, and those proved actually pretty good. And in about 2000, we got funding from the Federal Highway to do a demonstration project. And that demonstration project, we seismically retrofitted the State Street Bridge in Salt Lake City underneath I-80. And when those other bridges were replaced with ABC methods, that was the only bridge they didn't demolish. The State Street Bridge is still there, and it's completely wrapped with carbon fiber as a seismic retrofit. So we had a good experience with carbon fiber polymers, and we said, let's try that on these piers. So just a little introduction for those of you who are not familiar. Carbon fiber reinforced polymer is lightweight, is corrosion free, has a higher tensile strength as steel. It can be molded to any shape, but it does have a lower modulus of elasticity than steel. So in this work, we actually use quite a few different types of materials. We use a carbon fiber sheet, as you can see here, which is a laminate. Then we use carbon fiber anchors, and we use these in a couple of ways, as I will show later. It looks like a braided thing, and that's what it is, but it's very strong. You can see here the capacity tensile strength 165 ksi, tensile modulus 15,000 ksi. But of course, the downside is tensile elongation is only 1.1%. And the anchors we used were 3/4 inch diameter. We also used, for our second retrofit, carbon fiber reinforced polymer near surface mounted bars. These look like fiberglass rebar, but they're actually carbon fiber. And they have high tensile strength, 300 ksi. That's almost 5 times stronger than steel. Tensile modulus, though, is a little lower than steel, 19,000. Steel is 29,000. Tensile elongation is the biggest problem, 1.6%. For example, steel bar can go up to 10%. So it's a little bit low for strain. And these carbon fiber bars were about 1/2 inch diameter. And the carbon fibers reinforced polymer laminates, this is the sheets. Tensile strength is still good. It's unidirectional fiber in this direction that you see my cursor going up and down. It has very high tensile strength, 180 ksi. Tensile modulus is pretty low, 10,700. But the biggest problem is tensile elongation, 1.7%. And the thickness is very thin, 0.04 inches. But it does very well in confinement. So let's start with the third test, which is the wall pier that we retrofitted with carbon fiber vertical anchors. So to clarify, retrofit means we did this before we subjected the specimen to an earthquake or simulated earthquake. So here you can see the retrofit. The original cross-section is the same. But in order to overcome the lap splice issues, we use vertical anchors. These are about 9 3/4 inches. Actually, they are 9 anchors, then they are 3/4 inches in diameter. There are some challenges trying to drill into the footing here. Yeah, those are challenging to drill, but they're mainly there to take the tension in the lap splice. The other thing we did before we put these anchors, we put vertical sheets to take tension in this direction, because as I told you, the steel in this direction was actually very small reinforcement ratio. And we also found that if you sandwich these anchors with 2 layers of sheets, they actually perform very well. In addition, to improve the shear friction capacity of the lap splice, we use horizontal anchors through the 12-inch thickness. You can see it here. 2 layers. Each layer, that we call these transverse anchors. Each layer has 5 anchors. These anchors are 3/4 inch diameter again, and they are splayed, as you see, 360 degrees. Below the anchors and above the anchors, there is also carbon fiber sheets in the hoop direction, meaning going all the way around the wall. So there are quite a few layers of those. There are 4 layers for the first 2 feet, 2 layers for the 1 foot above, and then the other 4 feet is just 1 layer. So there's quite a few layers here, but the bottom 2 feet is reinforced pretty heavily. So here you can see the anchors that are sticking up about 18 inches, and they overlap each other. There was 9 of these on each side of the wall. So the idea here is to increase the flexural resistance by creating a positive connection between the footing and the wall, almost completely ignoring the steel that was there, which wasn't much, as we saw in the first test, because it was a lap splice failure. Here you can see the transverse horizontal anchors. Here you see a couple of them I put in the circle. It's kind of hard to see, but you can probably make out there are 5 in each row. The first row is 6 inches, the second row is at 14 inches, and so on. Then there is a layer below, confining layer of carbon fiber, the anchors, and then there is one above. So we found out in previous work that if you sandwich the anchors, actually it makes them very strong and very hard to fail. So, I mean, these anchors help with confinement as well, because this is a very long wall. It's 4 feet long, and they increase the clamping pressure on the lap splice bars, and they also increase the confinement. So the confinement is very easy to see, because if you have a 4 foot by 1 foot wall and you go around it, your confining area is what you see shaded. But if you put these transverse anchors, now you're cutting that area into 5 pieces. So it's actually much more manageable, and it's much easier to confine the wall in the transverse direction this way. In addition, the anchors serve the dual purpose of putting pressure here, putting confining pressure into the lap splice bars. And every time you have pressure here, when you put tension on these bars, it's much easier to pull them apart, much harder, because of shear friction that you're creating with this pressure, the transverse pressure. So here is some picture that shows the bottom 4 layers of confinement, then this area with 2 layers, then the one area with 1 layer. And of course, you also see the 1 layer which is vertical for improving the flexural capacity. So these are the vertical anchors then. There are 9 of them on each side. There is 2 sheets, 1 on each side. There is 10 anchors, 2 rows of 5. And then there is a 4, 2, and 1 hoop direction carbon fiber sheets. So this is the specimen for the retrofit one. So what happened? This is what happened if we compare it to the first test. You see we improve the lateral force from 15 kips up to about 25. We improved a little bit the displacement capacity, but not much. But unfortunately here, I'm going to show you this drop is because one of the anchors actually pulled out from the hole where it was. So this was a little bit of a construction error on our part. The epoxy that was supposed to hold it in was not placed correctly. And so, as you will see, it pulled out, and in that case, it failed on one side of the wall. The other side of the wall, nothing failed. So it's really very good. And you can see here, of course, these are debonded areas, these little circles that you see where we hit it with a quarter and we can hear, or a washer, we can hear it's hollow. That means the carbon fiber is debonding from the concrete. But here is the main failure, which, as you saw, the anchor here failed at about 2% drift ratio. One of the anchors, it actually failed. The lap splice actually wasn't too bad, because as you can see here, the footing bar and the wall bar, first of all, the strain is very small. They never yielded. So it's almost like the steel wasn't there. It didn't matter it was there or not. So I would say that the retrofit was successful. And the second one was a retrofit using the near surface carbon fiber bars. And here you can see these bars. They're 1/2 inch, as I said. We drilled again into the footing and they go all the way up. And the way we drill this is we drill it into the concrete. I'm going to show you a cross section in a minute. Other than that, we had a similar situation, 10 horizontal carbon fiber anchors, 3/4 inches. We had a vertical, actually we didn't have any vertical sheets because these carbon fiber anchors are very good in tension. And we had only the hoop layers, 4, 2, and 1, like I showed you before. So in this case, instead of 18 carbon fiber anchors, we had 18 vertical rods. And everything else is pretty much the same. Here you can see Vanessa applying those the resin for those anchors. And the hard part, of course, is to drill into the footing. And that's pretty difficult, but it's difficult even with the other anchors, the splayed anchors. So yeah, it will give you a little bit of trouble trying to put it into the footing. But it does increase the flexural resistance and will create a positive connection between the footing and the wall pier. Here again, you see the anchors, the transverse anchors that we talked about. And here you see the 4-2-1 layers for confinement. So here is the result. You can see that this specimen again went almost to 25 kips, but unfortunately this one again at around 2%. We had one of those near surface mounted rods pull out of the hole because the resin that we put in there was not packed correctly. On the other hand, the other side of the wall did just fine, because in that case the anchors were actually packed correctly, and you can see we achieve our goal. And here we saw it in the video. You can see here that the resin pulled out from the concrete. It didn't bond very well to the concrete in the hole, and we got these dust clouds that came out. And you can tell it's because we didn't break the rod. The rod is very hard to break, but the rod did pull out from the hole because the resin in the hole was not packed properly. And again, here you can see that the lap splice did very well actually in this case. It's almost like it didn't matter. So as a summary, for the as-built, the load was 15 kips. Both retrofits achieved 26 kips. The drift ratio for the as-built was 6%. The one with the anchors went to 7%. It was a little better. The near surface was 6%. But what is important here, perhaps more than anything, is the energy dissipation. The energy is the area of these curves, because this is force, this is displacement pretty much, and you can find out the area. That's the energy the specimen would dissipate in an earthquake. And you can see that the as-built only dissipates about 500 kip inches, whereas both retrofits were above 800. So this tells you that the retrofit actually makes the wall much more resilient when you have an actual earthquake, and it actually worked. And the failure mode was lap splice. Here we had the anchor fail, and here we had a bond failure of the NSM bar. Now let's look at repair. So we had the original specimen, the as-built. How will it perform after an earthquake occurs? So if we have it, there is an earthquake, you didn't retrofit it, can you fix it? Can you repair it now after the earthquake so you can keep the bridge open? The same question is for the modern code wall pier. Okay, it's a modern code. You had an earthquake. You design it according to the code. Can you fix it now that it's been damaged due to an earthquake? And I have to say, the damage due to an earthquake, as you can see here, is very severe. I mean, when I show you this wall, and I'm going to tell you, for example, the modern one, we had a bar break here. We had a lot of concrete spalled. Can you repair this? That's the question we're asking. That's a pretty tough question. And let's see how we did. So first, we will start with the as-built, the one that was deficient, and we tested it and we failed the lap splice. And we learned something. We learned that if you use the carbon fiber rods as vertical near surface mounted bars, they're great, they're very strong, but they are not very ductile. So we decided to use mild steel vertical near surface mounted bars instead of carbon fiber. So you can see the situation is very similar to the second retrofit, but instead of using carbon fiber, you use just mild steel grade 60 bars that you can get off the lot, number 4 bar. So we had 9 on each side like we did before. We still use the carbon fiber transverse anchors though, the 3/4 inches, and then we did our 4-2-1 confinement. The same story that I described earlier in the hoop direction, going all around the wall. So you see here Vanessa, she's epoxying in, and again, drilling in to put near surface mounted bars is not that easy. This drilling into the footing, it's a hard story. But we learned our lesson and we try to do this very professionally. We got a Hilti epoxy and we put it in, and this time you can see these anchors are very good. Also here you see the holes. We had to drill holes to put the transverse anchors, and those were carbon fiber. And you can kind of see them over here. They look a little blotchy, but those are the 5 anchors, first row, 5 anchors, second row. And then you see Bhaskar here also applying the carbon fiber sheets for confinement. And what happened is we had a little cracking in the footing, which was a good sign that something was working here. But you can also see there was some debonding near where the bars were, even in the bottom a little bit, but this is at 4%, so it's pretty good performance. And here you can see the original test 1 of the deficient wall pier that went to 6%, 15 kips. When we did the repair, you can see the repair actually went higher, went to 20 kips. And it only went to 4% drift ratio. 4 inches is about 4%. So it didn't go as far as the other one, but it actually maintained pretty well its performance. And then when the bar debonded, it actually pretty much followed the old one. But just remember, this is a repair. This is almost like, you know, rebirth of the wall pier, because this was damaged and now we're actually repairing it. And if we compare the numbers, we went from 15 kips for the as-built to 22 for the repair. The drift ratio at the peak was 4%. We went down a little bit, 3%. Ultimate was 6. We went down to 5. The failure mode of the original was the lap splice failure. And as far as the repair, we debonded the mild steel bars. Yield force was roughly the same. Stiffness was much stiffer for the repair one. Yield displacement about the same. Ultimate displacement a little bit less for the repair. And the ductility, which is the ratio of the ultimate to the yield, was 7 here and was 6.5 for the repair. But to give you an idea, 6.5 is not bad. For example, Caltrans doesn't want you to design something with more than 5. So 6.5 is good. And then the last test I'm going to show you is the repair of the modern code compliant wall pier. This is the one that was really damaged. And here we use the method we actually developed in a previous project. And this was also funded by MPC, something we call the donut. So the donut, we did it there for columns, but we tried to replicate it here for wall piers. So what it is you forget about everything inside the wall, all the vertical steel, and you try to replace it with headed steel bars outside the concrete of the wall. And then you make a carbon fiber shell and you fill it with concrete grout. It's as simple as that. What you're doing is all the damage area in the plastic hinge on the bottom, you try actually to fill it with concrete and vertical steel bars that will transfer the tension to the wall that's not damaged, and you're moving the plastic hinge right above the donut. So I'm going to show you, and then you will realize this is a donut, but it's an elliptical donut and not a circular donut. Because remember, our wall is 4 feet by 1 foot in cross section. So here it's actually drilling is easy because you drill away from the wall and you put in the headed steel bars. These are grade 60, very easy to install. Drill the hole, put a little resin first, then push it in until you see the resin come out. Then you know that this was done properly. Of course, we also use epoxy injection to close any cracks. But you can see we didn't do anything down here. We didn't patch the concrete or nothing, because that takes a lot of effort. Instead, we build the donut and then we fill it with grout. But the donut, of course, is very strong for confinement, has carbon fiber layers that are many, and so it protects all this area and will force the wall to actually fail above this area. We call this moving the plastic hinge up. Sometimes the grout doesn't bond very well to the original wall concrete, so we build this steel jacket or steel collar and we put some studs on it. So the concrete grout that goes in here will actually bond to the concrete. So for example, the wall had a compressive strength of 5,000 psi, and the grout ended up being close to that, about 4,500 psi. So sometimes they won't bond automatically. So if you do this collar, it's not that difficult. In fact, this steel collar can be built very easily for those who know how to weld by just welding and letting the weld cool down. When the weld cool down, of course, the steel tends to shrink and it clamps onto the concrete. So there's nothing to it. There's nothing else holding up this steel collar. These studs poking out here, they will grab onto the new grout that you pour inside the shell. So how do you make the shell? Well, we use an aluminum foil and some wood formed, and we made this big circular or elliptical tab, as we call it, the tab, instead of a donut in this case. And that makes the form work. And then you wrap this aluminum foil with the carbon fiber sheets, and then you can take out the wood and the aluminum foil. When in about 3 or 4 days, this carbon fiber actually hardens. It hardens very hard. It's almost like glass. You have to be very careful. You can cut your fingers. So this is what it looks like in cross section. This is the original 1 by 4 feet wall. And you see we ended up with a 30-inch by 60-inch tab here. We have 9 hoop layers of carbon fiber. And we found in previous tests that we did, actually again under the Mounted Plates Consortium, if you put a vertical sheet, that helps you consolidate the stresses that this carbon fiber is going to see, because some of the times you have a little bit of a vertical action. So it's good to put at least 1 vertical layer on the outside. And here you can see number 5 headed steel bars. There's 5 on this side, actually 6 on this side and 6 on that side. The area of this kind of is equal to the area of the original steel inside. So you have to be careful when you do this, because the original moment demand was down here. But now that you put this donut, your demand, of course, increases. So you have to be careful when you do retrofits like this to protect the wall so you don't exceed the capacity. So here's the performance of the hysteresis of the repair. You can see the repair is pretty large, and it went all the way to 6%. So definitely satisfies the code, even the current code, even the Caltrans code. And you can see, as we predicted, we failed the wall above the donut. Nothing failed inside the donut. Everything was above the donut. You can see it here at 5%, and you can see it here at 6%. And we could have gone even at higher drifts if we wanted to. All we had to do was put carbon fiber layers on this wall, but we didn't want to go above 6%. That was plenty enough for us. So yes, you can see that, in fact, we increased a little bit the strength from 30 kips to 35 kips. Performance is pretty good, up to 6%. So the repair, I would say, is very successful. Here you can see how the strains in the jacket of the carbon fiber shell go up. And this is roughly where the top of the headed bars are. And as those bars are pushing out, you get tension into the collar, the carbon fiber shell, and you can see that tension increases as you go up to 20 inches. So it makes sense that it behaves like that. On the other hand, the strain is very low. It's almost half the capacity of those sheets, which I told you is about 1.2%. This is only 0.6%. So as a comparison, what was the modern code compliant? Was 31 kips, 32 say. The repair was 36. The drift at the peak was 8. Here we got to 5. The ultimate was 10. Here we got to 6. The failure mode in the original was west bar fracture. Here we saw a little buckling of the wall bars above the plastic hinge. Yield force was 30. Here was 34. Stiffness was 21. Here less, 20.8. Yield displacement about the same, 1.8 inches. Ultimate displacement was 9.6 here, 5.6 here. Ductility 5.3 here, 3.2. So I would say this was a good repair. And I summarize the conclusions, because there's 6 tests here, and there is retrofit and then there is repair. I summarize in 2 groups. Let's talk first about the retrofit. As build wall specimen was not able to develop the theoretical capacity because the lap splice failed. The retrofit, the first retrofit with the vertical anchors and transverse anchors and vertical sheets and hoop carbon fiber sheets, that was the first retrofit, R1. It dropped after the first cycle at 2% drift because two of the vertical anchors fracture on the west side of the wall. On the east side, though, where the wall, the anchors didn't fracture, it behaved very well. Actually, this retrofit performed better than the as-built and reached a drift of about 7%. So the retrofit at the 2% ratio, where we see the first drop, had 2 times the initial stiffness, 1.6 times the energy dissipation, and 2 times the flexural capacity of the as-built. How about the second retrofit? To remind you, the one that had the vertical near surface mounted carbon fiber bars. It also had the transverse anchors. It also had the carbon fiber jackets. This one was good up to 1.5% drift ratio on one side, where 2 of the near surface mounted carbon fiber bars debonded. And of course, this can be prevented if you have very professional crew installing these bars. But on the other hand, it behaved well and resisted the increased lateral force where the near surface mounted bars didn't fail. The jackets and the anchors were intact and did not experience any crack until 7%. So the retrofit of R2 was about 2 times the initial stiffness, 1.7 times the energy, and 1.6 times the flexural capacity. So I would say these two retrofits were very equivalent, and probably these near surface mounted bars, if we were to install them properly, would have done very well. But I would say they were successful. They give you some alternatives for increasing the flexural strength in an economical and very fast manner. I mean, remember, I'm working with 2 students in the lab and we're doing all this ourselves. So I think to make it more efficient, probably the jacket has to have an increased number of layers to provide more confinement and improve the ductility a little bit more. How about the repair? So first, the modern code compliance specimen was able to develop fully its theoretical flexural capacity, which is good news for the existing codes, and perform very well up to a drift ratio of 10%. The deficient one and this modern code were repaired after significant damage. Especially the modern code had a lot of damage. We broke the bars. But even the as-built deficient one had damage because the lap splice failure. So the as-built one, the repair actually of the as-built one failed in the cyclone cycle or the 4% drift ratio because of debonding of the mild steel near surface mounted bars. I still think the mild steel near surface mounted bars are better than the carbon fiber because they actually give you a little bit more resistance before they break. So the repair of the as-built specimen performed better than the as-built specimen, even though it was repaired, with increased stiffness, lateral force, and hysteretic energy. How about the repair of the modern code? The repair of the modern code, we use a very rapid seismic repair method. We use what we call a plastic hinge relocation with that carbon fiber shell and the headed steel bars. This repair was applied successfully and restored both the load carrying capacity and the stiffness of the damaged reinforced concrete wall pier with a cross-section aspect ratio of 4. So the repair method was able to strengthen the damaged region considering the additional bending moment and shear. No failure was observed in the repair region of the system, and the shell was intact. It did not experience any cracking, and it continuously provided confinement and shear strength to the repair. So the repair specimen matched the displacement capacity and energy dissipation of the original modern code compliant specimen up to a drift ratio of 6%, and we didn't want to go above that. So that's my lecture. I want to acknowledge the Mountain Plains Consortium for the funding, MPC Project 526. You can find this report on the Mountain Plains Consortium website. Our collaborator in the carbon fiber area was Structural Technologies. We have generous donation from Geneva Rock for the concrete and the headed steel bars from the Headed Reinforcement Corporation. I want to also give congratulations to our laboratory manager, Mark Bryan. And also I want to acknowledge the assistance of other graduate students, Ryan Barton, Colton Murphy, and Duke Tran. So with that, I have here the references of everything that I talked about in this paper. These are works that have been done before, none to the level that we did though with our scale specimens. These were half scale, so they're kind of large and almost very real. And so you can see all these problems that can arise. And I want to thank you for your attention. And if you have questions, I'll be happy to answer them. I think we have about 15 minutes.
Thank you, Chris. Appreciate you sharing that information. If anyone does have any questions, you can either unmute yourselves and ask the question, or you can certainly type it into the chat and we will ask your question for you.
I hope I didn't go too fast.
No, you
I have
did
a
not.
tendency to roll like a river, but I know this topic is very interesting because for your area, if you have bridges that look like this, typically they are not well designed if they're about the age of the ones that I showed, because they have this problem down here at the splice. This lap splice is very deficient. And in fact, I know for a fact UDOT is tearing down these wall piers. This is a picture near St. George, Utah. And the reason they're doing that is not because of the seismic. I think the seismic is a secondary concern, is because they're widening the bridges. So when they widen this bridge, actually, they didn't use wall piers. They actually use bridge bends. They use 3-column or 4-column bends with a cap beam. So nobody wants to ask me a question.
No.
Am I too perfect?
I think we'll just go with that. Yes.
I am. Well,
I think we answered a lot of questions early on yeah. Before we started. So
sure.
With that, thank you again, Dr. Panelides. Thank you for sharing this research. We look forward to working with you here again in the future. Don't forget to visit our website at translearning.org to see upcoming learning opportunities, as well as to see the future topics that we are currently working on. So Chris, the question that's out there is, can these designs be used in non-seismic areas?
Oh, absolutely. Yeah. Absolutely. These designs can be used because even if you, in a non-seismic area, sometimes you need to reinforce the pier or the column for capacity because of increased truck loading. For example, in Utah, we still have a couple of bridges on Foothill in Salt Lake City, which is near the university, which actually the engineers at UDOT asked us to wrap them with carbon fiber, the columns, just because the trucks have gotten heavier. And they are worried that these columns are not going to be able to sustain all the new traffic loads that we're seeing. I was lucky enough to participate in a construction of a new bridge on US 6 in Utah on the way from Salt Lake City to Moab and then Colorado. And then we measure actually the weight of the trucks, and you will be surprised. I mean, we're designing for 32 kip axle loads, and we saw trucks that weighed more than 124 kips. That's 124,000 pounds. And so there is much more loading now than when those bridges were designed. So yes, these materials can be used to strengthen existing bridges that are non-seismic areas. Also, I mentioned the other issue. How I got involved with carbon fiber is because in Utah, they wanted to replace some corroded bridges and they wanted to buy time. So if you want to buy time and you wrap it with carbon fiber, that will buy you some years before you can get to it. And at least you know that the bridge is not going to collapse because of traffic or whatever other reason other than seismic.
And I would say geohazards would be also an applicable area. And in our area, we do deal with some sliding surfaces. So I think that would also be, I think, something that would be considered. Maybe I'm off, Chris, but I think that would be something
Yeah,
where this is
sure.
obviously
No,
applicable.
absolutely.
Hmm.
Yeah, in fact, yes, in fact, I'm aware they use glass fiber, not carbon fiber, because glass fiber is much cheaper. And I think there is a question about how does the economics
Yeah,
compare to standard
yeah,
designs. Thank you for that question. So in southern Utah, they went underwater because of the scour issue that you mentioned, and they wrapped the columns with fiberglass. And that strengthens the area there as well. But as far as the economics, I will tell you this: 30 years ago, it was very expensive to wrap these columns with carbon fiber. These days, it's actually very competitive. With, for example, if you wanted to repair this wall pier, let's say that take the modern one, and you wanted to use a reinforced concrete jacket, you would have to chip all the concrete out, put a form, and then put new rebar and drill and do the same thing with it. And that would cost you probably more than it cost you to buy the material. Yes, the material is more expensive. It's probably $10 a square foot. But if you want to do it the traditional way, it will take you much longer. It would take you months to do a retrofit like this. We did it in less than a week. So I think there is economics of scale and economics of size. And the material, yes, is more expensive. And yes, it requires a well-trained crew to do it properly. But I think the price is very competitive with traditional methods.
did you see that last question on there as well when you mentioned the truck loading?
Oh
And I would
yeah,
say it kind of depends on the
yeah.
area.
In fact, I can talk about that. I
Yeah.
think we had a camera, and the camera would take snapshots, and we had almost a weigh-in station where we would weigh the trucks, and as they came up the hill, we would measure the acceleration, and so that's how we knew that this truck was causing havoc on that bridge. That bridge didn't have columns or wall piers; it was just a simple span with integral abutments. But we were surprised because at nighttime there was construction in the area, and I think some of the loads were permitted, but some of the loads were illegal because they would drive those big haulers with equipment on it at night. And at night, our camera unfortunately didn't work. So I can't prove it to you, but indirectly, I can prove to you even the ones that we weighed exceeded 124,000 pounds. And I know from our research in that instance, it's not the total weight that matters, it's the axle. But how many times does that axle go over your bridge? I don't know. So this is something I think people like you guys know better than I do. But
Probably, yeah, Kelly, I think you're right.
I mean, yeah, everybody has a way to get around a loophole, right?
The one that I see often is when there's truck inspections at the rest area close to me. the
Yeah.
the local road gets busier with truck traffic than the interstate does. So
Well, and in fact, for this study, we were also able to measure with the LiDAR gun the speed of the truck. Not only were we measuring the acceleration, we knew the weight from the weighing station down the hill. And as we saw it coming, we were able to actually catch the speed. And I can tell you, it was more than the legal speed limit. And when they saw our gun, they would slow down, but it was late by then. They already went over the bridge. So, I mean, you know these tricks. So yes, get me a badge in the car with a star on it. Yeah, I understand what you're saying. So you will be surprised what you can find out.
Okay, well, very good. Well, Chris, thank you again for your time today, and thank you everybody for participating in today's TLN event. We certainly do appreciate that. With that, again, thank you everybody. We certainly appreciate your time. Stay safe and don't forget to be awesome. Take care, everybody.
Thank you, Chris. Thank you, everyone.